Hello, my name is Marina Lima Medeiros. I am a researcher at VRVis Research Center in Austria and a PhD student at TU Vienna. I am excited to present the design, implementation, and evaluation of a collaborative VR application for tactical resource planning on spatial data. Tactical resource planning is a common task executed during a military staff exercise, a simulation-based training that involves interdisciplinary high-level military personnel. Participants work in groups under the coordination of a commander to plan tactics based on a fictitious crisis, for instance, peacekeeping, humanitarian operations, rescue tasks, or defense. A standard tool used for the decision-making for tactical planning tasks are 2D or 3D maps. Though 2D maps have some evident shortcomings. First, there is limited support for height information. Other terrain information, for instance, slope or height, is complex to read. Users often rely on depth cues communicated through shading or surface topologies to derive information. Current paper map alternatives can be grouped in three categories: desktop-based displays, projection-based setups, and head-worn displays. Compared to the other two, head-worn displays provide increased spatial understanding through higher immersion, 3D perception, and realism, and in relation to 2D displays, improve the perception of complex structures. In this work, we focus on the design of a three-dimensional planning environment for tactical resource planning, leveraging the advantages of immersive systems. First, we held consultations with experts of the Institute of Military Earth Science of the Austrian Army. With them, we discussed basic technical requirements, such as the data format and structure of the terrain data. Further, we conducted a field study in which we passively monitored the behavior of officers during a staff exercise. During mission planning, all groups work on a current task collaboratively. Every group was dedicated to the staff of one discipline, for example, intelligence or logistics. The result is drawn on a transparent sheet overlaid on the map. The officers present their tactics to the commander using the transparent sheets created during mission planning. The commander then gives them feedback and suggestions. From the initial field study, we decided to implement an asymmetric collaborative setup, a system that supports different resolutions of terrain data, and we defined two use cases for our application: terrain annotations, inspired by the transparent sheets, and visibility and quantitative analysis of terrain information. Our prototype is based on the game engine Unity. At the start, we imported terrain data, previous annotations, and project-relevant metadata. The annotation information can be exported by the user anytime. As you can see on the right image, two users can work with the system at the same time. The desktop operator can see a mirrored view of the VR user and interact with an orthographic top map view. We implemented different awareness cues to support users' collaboration. A pointer for the VR user used to query terrain and annotation information. Further, the desktop operator can observe the position of the VR user on the map and see a first-person view from the current gaze of the VR user. As you can see on the bottom right, the VR position and gaze are shown in the map view through an avatar. Overall, the work environment for both users is synchronized. We will now show a video with the features of our application prototype. In the video, the desktop map view is represented on the left side and the gaze of the VR user is on the right side of the screen. This video shows what a desktop operator would normally see using the application. You will see both users working together in a synchronized environment. For the locomotion, we implemented three different techniques: standard teleportation for short distance traveling, 3 degrees of freedom steering, and the world in miniature metaphor for long-distance traveling. Based on our field study, we implemented features for two use cases. The first one is map annotations. Overall, we assigned the annotations to layers, which resembles the transparent sheets used in the staff exercise. We implemented 4 annotation types: points, polylines, polygons, and standardized NATO markers. Both users can place those annotations on the terrain. The second use case uses features for quantitative analysis on the terrain. Both users can query distance between 2 points or area of a polygon using mouse or raycast input. We also provide a line-of-sight visualization feature. The user in VR can drag a wide sphere to choose a location on the map. From this point, the line of sight of that point is shaded in green. To evaluate our prototype, we conducted semi-structured interviews with 3 cartography experts. Prior to the interviews, the experts were able to field test our prototype at different staff exercises in second and third quarters of 2021. The interview suggests that VR provides an enhanced understanding of terrain data for non-domain experts. Some implemented features stood out as especially useful for tactical planning on spatial data, for example, 3D drawing and terrain measurements. Last, using the VR environment, users can place annotations more precisely. In comparison, on paper maps, annotation could occlude other information and have a fixed resolution. Further, the potential is dependent on non-technical circumstances such as user attitude, prior experience, and interoperability. In future work, we want to improve the interoperability of a VR system with other software to allow an uninterrupted working process. Also, due to the COVID-19 pandemic, we were not able to perform a user study. So in future work, we will include a quantitative and qualitative usability study to understand the bottlenecks and merits of our 3D interaction design. We would like to thank you for your attention, and we are eager to discuss more about our findings and answer any question.